Okay, welcome everybody to the 17th of December installment of the INQA online seminar. Gives me great pleasure to introduce Henning Schloemer from the University of Munich, who's been collaborating with Sachdev at Harvard, and he's going to tell us all about quantum annealing with chaotic driver Hamiltonians. So over to you, Henning.
Yeah, hi everybody. Thanks a lot, Paul, for this invitation. I'm really excited today to talk about a very recent project where we take the regular quantum annealing schedule and we replace or add to the transverse field, which is typically used, chaotic driver Hamiltonians, and then see if we can get some boost in performance here. And so most of you will be very familiar with this, but just to bring everybody on the same page, a quick recap of the usual transverse field driver Hamiltonian. So the standard quantum annealing process here, you have some classical optimization problem encoded in some Ising model, which is scaled with the parameter S. And then you have the transverse field, which is simply the sum over all the sigma x terms here times 1 minus S. And then when you change S, you will essentially gradually go from the transverse field over to your classical Hamiltonian. And now the transverse field is kind of a natural way to implement quantum annealing because it gives you a Hermitian complete combination of operators that couple all classical bit strings in your search space. So hopefully you will be able to make kind of a broad search through your parameter space and then find the global minimum or maximum. So what it boils down to in the end, if you want to compute a quantum annealing, say using classical methods, is that you have to do unitary time evolution under this time-dependent Hamiltonian here, where S varies as a function of time. And what's particularly nice about this schedule here is that it is a stochastic Hamiltonian, which is just a fancy word for saying it's sign problem free. So basically, you can use quantum Monte Carlo in order to simulate this. Now, QMC is made for equilibrium properties, but nevertheless, if you interpret your sampling as some sort of time, then you can indeed, when continuously changing the parameters in your Hamiltonian under which you sample, you can actually get the main, say, essential properties of unitary time evolution also using QMC. And so this has been shown for a variety of settings. So you have a spiky optimization landscape, say for 2D Ising spin glasses, traveling salesperson problem, 3-set graph problems, and many more, where this is really substantially quicker compared to simulated annealing, which is the fully classical version, where you only have this classical Hamiltonian, and you anneal down in temperature and do fully classical Monte Carlo simulations. Now, on the other hand, you can turn this argument around and say, well, if I have a problem which is very hard to solve using the transverse field driver, which I can classically simulate efficiently, then it will also be hard to do that on dedicated hardware, which really implements this unitary time evolution here using the transverse field. And so this has been addressed in also a variety of works. I just want to highlight one particular work here, where they look at the annealing time as a function of your problem size of the bits essentially. And they look at the scaling of this annealing time for QMC, which is shown here in green, and the D-wave machine directly, which is shown in blue. And then simulated annealing is shown in red, which is the fully classical version. And you will observe that indeed for QMC and D-wave, you get very similar scalings here, which is also expected from what I said earlier. However, you can, of course, have a substantial difference in the prefactor, say. So you can get a constant speedup, but the question really remains, can we do better than that? Can we somehow add additional terms to this Hamiltonian in order to be better? And so to kind of introduce what we did with the SYK model here, let's first define what we mean by hard instances when looking at the transverse field Hamiltonian. And so for these hard instances, we then want to add other terms to the driver Hamiltonian, which cannot be efficiently simulated classically, and then hopefully we get some speed up in some sense. Okay, so the basic definition is we take the quantum annealing schedule here, which is just given by the transverse field, the classical Hamiltonian. And then, and this is from this archive article here from 2014, which did some problems here on some graphs, some 2-set problems. And basically what they look at is the probability of actually ending up in the ground state of your problem after some given time, which here is 100 times the typical energy scale of this classical Hamiltonian here. And then they look at basically a histogram of different instances of your graph problem, how often you get certain probabilities here. Certain accuracies. Okay, and if we look into this in a bit more detail, say for a particularly hard to solve problem where we have very low probability of ending up in the ground state here at some intermediate times, we will observe that at t equal 100, it's heavily suppressed. But then it turns out if you go to lower annealing times, you get this diabatic peak. So you have kind of locally an enhanced probability of ending up in the ground state, which really defines this property of being, hard to solve. You have this diabatic peak, then it's suppressed, and then at very, very long times, it will go into this adiabatic regime and then start to go towards 1 exponentially. And the intuition here is that if you have a very small instantaneous energy gap between the ground state and the first excited state in your annealing schedule, you will very likely transfer your weight from your ground state to the first excited state here, which is really not what we want to have in the end. And so if you go fast enough, the intuition is that before the gap closing, you already have some weight transfer to the first excited state. And then at the avoided crossing, you will actually go back to the ground state and hence have some enhanced probability of ending up here. Okay, and so what people have looked at is if you can basically get better performances when adding additional terms to your quantum annealing schedule. For example, what has been studied are these two local terms. So you have this kind of sigma x-like interactions, which kind of live on the graph. And indeed, it has been shown that adding these non-stochastic Hamiltonians and also for other stochastic ones with two local terms give you an enhanced success probability for these intermediate times. So it seems to promote these diabatic transitions at low times, giving you a higher probability to be in the ground state. And similar findings have been reported here for non-stochastic AFM couplings, basically with the same kind of conclusion here. And changing gears a little bit, I just want to mention this because I think it's a very nice result. It has also been shown for a very particular optimization problem, which is the p-spin problem, that when adding AFM fluctuations, you can actually change the nature of the phase transition. So you start off in some disordered state, and then you end up in some spin glass state, say. And so you will encounter some phase transition, and it has been shown that a first order can actually be changed to a second order phase transition by adding these additional fluctuations, which then gives you an exponential speed up because your gap closing does not go exponentially anymore, but only polynomially. All right, so we can now try to build up some intuition on which terms we should include in our quantum annealing schedule in order to get good results. And of course, the intuition here of quantum annealing is that you have these tunneling events. Say you have some state here, which is separated with some other lower energy state here by some energy barrier. And if you have quantum tunneling, you can tunnel through this and kind of stay at a constant energy and then explore the search space. However, what happens if you have a very wide energy barrier here, you're kind of forced to go back up in thermal activation. So you cannot tunnel through it anymore. It's exponentially suppressed. So you really have to go up in energy and then swoop over and then go down again. And so what we can basically do in order to potentially enhance this is to include multi-point interactions, so denoted here by this number q, that couple larger Henning distances. So on an intuitive level, you can imagine that your energy landscape, where you have these energy barriers with width w, which for the transverse field basically is just given by the Henning distance. And if you add these q larger than 1 terms, you can imagine you kind of reconstruct the energy landscape and your widths may become smaller. And similarly, since the whole essence of quantum annealing are quantum fluctuations, you may also think that adding a higher degree of quantum fluctuations and then non-commutativity may enhance some interference effects, which may also help you. So before actually going to the SYK model, which will be the main theme of my talk, I want to give a very, very easy kind of toy model here that just has 2 spins. So imagine I have an up-up state, which has some small energy. The global minimum is the down-down state. And then the up-down and down-up state will be gapped out here heavily in energy. And now if I use the regular transverse field Hamiltonian and look at the instantaneous eigenspectrum energy gap, so the energy difference between the first excited and the ground state, we will find that there's a local minimum somewhere here, which is quite small. And hence, we need some relatively long time in order to get large populations here in the ground state, which is simply because we start in the transverse field, so we have equal weights here on all these 4 different points, and then we somehow need to transfer this weight through these very spiky peaks all the way here to this green point. Okay, so now I can think about adding these higher Q terms. So let's say I add something like sigma 1x, sigma 2x, and now it turns out actually that it doesn't help us at all. It closes the gap here in this instantaneous eigenspectrum, and therefore our ground state population will be heavily suppressed here, even at quite long annealing times, and we have to go to extremely large times to go back to the adiabatic limit, and therefore get values close to 1 here. So that's something we certainly don't like. And indeed, you can write down this also analytically and kind of make some expansion and then see if you add this term that in fact your ground state will have the tendency to be suppressed. However, if you add this term now here with a different sign, so you have a negative sign here and then sigma 1x, sigma 2x, now we have the different situation. So here we actually open up the gap in my instantaneous eigenspectrum, and the annealing performance will be much better. So we will converge towards the ground state here much quicker. And now you can say, okay, well, if I add a positive sign, I have a negative effect. If I add a negative sign, I will have a positive effect. And I don't know that a priori if I have a general optimization problem. So I would probably do best if I just choose these type of terms here in my Hamiltonian randomly. Fully generally, you can say I add these Pauli matrices with different orientations, X, Y, Z here, and then I add these couplings here fully randomly, and then hopefully I can do better in some instances. And so here, what we did was just pull 10 different random configurations and take the best one, and we can see that in this case, we actually get a very nice performance and a much quicker convergence towards the ground state compared to the regular transverse field driver. Okay, and so this motivates the exploration of SYK-type physics and quantum annealing. So just to quickly define what the SYK model is, it's usually written down in this form where we have this Majorana fermionic operators, which have some Q-body interaction, and these interaction parameters are randomly drawn from some, say, Gaussian distribution around 0. And so this model has led to a large variety of insights from non-Fermi liquids to describe strange metal behavior in, say, cuprates, all the way to charged black holes. And also one thing to highlight is that it features many-body chaos in the sense that it saturates some bounds in how fast it scrambles quantum information. And so this model has been of high interest also in the field of quantum simulation. However, it's certainly very challenging to implement this in actual hardware because you have these fermionic Q-body terms. And so what people have been looking into recently is whether we can find similar models which also are bosonic that may be easier to implement on actual hardware. And one particular model is shown here where we basically replace these Majorana fermionic operators by the Pauli operators. And this now looks very similar to what I showed you earlier in this intuitive toy model. And then we again randomly draw all of these different parameters here. Okay, and so it has been shown that at least in some limits, if you have a large Q, so many body interactions, that indeed the 4-point function of this bosonic SYK Hamiltonian will be equivalent to the one of the original SYK Hamiltonian. So then you recover really full quantum chaos. I would say for a smaller Q here, there's still work to be done and things to be figured out. But at least it's a promising direction for models that may be more realistic to be implemented on quantum hardware. But the question that we really want to ask is, if we take this Hamiltonian here, can we use this chaotic nature of the SYK model to help us navigate through complicated optimization landscapes? And so here I will focus on mainly two optimization problems. The first one being the classic, the MaxCut problem. And most of you will be familiar with this, but let's very briefly recap what MaxCut is. Essentially, you have some random graph that you draw, and you may fix some connectivity. We here fix the connectivity to be 3. And then on these edges, you randomly draw numbers, say from 0 to 1, which is your edge weight. And now you're trying to find a decomposition of the vertices such that if you add up all the cuts between, say, the red and the gray vertices, you will maximize this number. And this can very naturally be mapped to an Ising model, a classical Ising model, which lives exactly on this graph, and these coupling terms here are exactly these weights on the edges. And what's nice about MaxCut, and I think that's also why it's so interesting for quantum hardware applications, is that you can very rigorously prove that it's an NP-hard problem above some certain threshold. So if you want to get the lowest energy state here of this MaxCut Hamiltonian up to certain precision, this is going to be generally an NP-hard problem. But I want to stress that there's many very efficient algorithms out there that give you very good answers on the heuristic level for most graphs. However, there are a few graphs which are particularly hard to solve, and that's exactly what we want to focus on here when testing this SYK-type driver Hamiltonian. And so this story will be very similar to what I showed you earlier. We basically take these n=14 graphs, and we randomly draw many of them, and we track the instantaneous energy gap, the minimum of it. And then we essentially only focus on the ones that have a very small minimum energy gap, which then give you very long annealing times and sort of hard to solve graphs. So one example I would like to show here is where this black dashed line is, where we have some energy gap of roughly 2 to the 10 to the minus 3. You will find when looking at the population of the different states in your final Hamiltonian as a function of annealing time, you again get this diabatic peak here at intermediate times. So let's track here this ground state population. Then it's heavily suppressed for some orders of magnitude. And then you will enter this adiabatic regime here, where the time is roughly 1 over delta squared. And to again look at some intuition here, you can imagine that you have some wide barriers in your optimization landscape where you cannot tunnel through anymore, and hence you really have to thermally activate and go up in energy, and that's intuitively what happens here at this avoided crossing. So you're kind of forced to go up in energy, and you cannot adiabatically explore, say, the optimization landscape. Okay, so the first kind of obvious thing you can try here is to simply replace the transverse field driver by this bosonic SYK driver Hamiltonian. And I'll comment on this in a bit more detail later. Certainly what you would have to do in an actual hardware implementation to start off at the ground state of your driver Hamiltonian, which is obviously very hard to prepare. So let's just use this as some kind of thought experiment here and see if it works better than the regular transverse field. And then later we can think about more realistic ways of implementing this. And what we basically focus on here is a time which we call T star, where the ground state population reaches a certain threshold, which we put to 0.9. And so we really want high quality solutions that can usually not be achieved within this diabatic peak. You really have to go to this adiabatic regime. Okay, and now we basically compare the T star we get from the bosonic SYK model, which is on the y-axis here, versus the T star we get when using the transverse field schedule. And so essentially everything that will be below this dashed line, which is where the two are equal, we will find that the bosonic SYK Hamiltonian does better. And furthermore, and this is primarily because of numerical limitations, we have some upper threshold here of the annealing time that we consider. So we only look into this time window here, and if we can find solutions within this time window, which I guess is also somewhat experimentally motivated if you have access to some given coherence time, say. Okay, and now we can look at the results here. So each of these vertical lines basically corresponds to one particularly hard graph of this classical MaxCut problem. And then we draw many different bosonic SYK Hamiltonians. We do the annealing schedule, and we check if we reach 90% within this time window. And if we do, we draw a cross here in this vertical direction. And what you can see strikingly is that independent on the kind of hardness of the optimization problem, when using the transverse field driver, you will always have situations or instances of your bosonic SYK Hamiltonian where you find solutions with really high quality here in sort of a more or less constant time, roughly 10 to the 3. And so let's look at this in a bit more detail. If we start off here with the transverse field driver for this hardest considered optimization problem, we can have this diabatic peak, then it's heavily suppressed. And now at large times, you can see it very slowly starts to rise and get into this adiabatic regime. So we had a cutoff here in our numerics at 10 to the 6. And then we very crudely approximate this to go to 90% at roughly 10 to the 10, which is not so important. The main point here is really that the bosonic SYK Hamiltonian gives you a vastly quicker convergence towards the ground state for certain configurations of it. So this is one particularly well-working example of the BSYK Hamiltonian here. Now this, of course, opens the question, well, if I have some bosonic SYK instances which actually help me get to the result quicker, how often does that actually happen in our experiments? And so we find that it's always about roughly 50 to 60% here for these mildly hard problems, say, and then for this very hard optimization problem, it's about 40%. So there does seem to be a trend towards lower probabilities of actually having a boost when you go to harder problems, but nevertheless, it's always a significant proportion of the bosonic SYK instances which give you a better performance compared to the transverse field. Okay, and if you look at the gap structure, you get the instantaneous gap structure of the BSYK schedule versus the transverse field schedule. You indeed find, and then I guess is expected also from these results, that the SYK driver significantly opens up the gaps and gives you sort of faster approach to this adiabatic regime here. And I guess the idea, if you would like to implement this, say if you have some logical qubits available and you can actually implement these bosonic SYK-type Hamiltonians, then the idea would be that you do the annealing with a variety of different BSYK drivers, and then you just simply repeat that many times for different SYK realizations, and then you simply take the lowest energy bit string that you get at the end of your sequence, and hopefully you will have encountered one of these instances which give you a much better performance and then a good solution. Okay, as I said earlier, I mean, obviously it's hard to implement or to prepare the ground set of the BSYK Hamiltonian. Certainly not easier than just preparing the ground set of your classical Hamiltonian. So what happens now if we change this quantum annealing schedule a little bit and we actually start off in the transverse field, and then we add these bosonic SYK fluctuations here kind of gradually. So in the middle of our sequence, we add these fluctuations and then we turn them off again. And if we do that, we indeed find very similar results. So there does not seem to be a very large dependence on the exact way we implement these bosonic SYK fluctuations here. The main point is more that we do include them at all. And here we can see barely any differences to what I showed you earlier. Okay, so the next question we asked is, now we did this for Q equal 4. So we have 4 body spin interactions. And now what happens if we change Q to say to be equal to 2? And in this case, we again find very similar performance. So we have many instances of the bosonic SYK2 Hamiltonian, which gives us a better performance. And also the ratios here of enhanced performance seems to be very similar. However, if you want to actually implement, these type of fluctuations here, you would have to implement a vast number of terms. So it's n to the power of 4 terms for Q equal 4, which is of course growing very fast. So you may want to consider only a linear number of terms, and you want to sparsify your Hamiltonian essentially and see if you still get this type of boost in performance. And that's also what we looked at here in this kind of last experiment, where we see that now the performance really looks quite different. So we still have a few of these instances which give us a better performance compared to the transverse field, but they are very rare and also not very significant. And these mean values, which are shown here by these diamonds of the successful instances, rather follow the line of kind of the point where the T star BSYK is equal to the T star X compared to what we saw here earlier. Okay, so it seems like these SYK type of fluctuations can significantly enhance quantum annealing. However, the density of these non-local terms seems to be more important than the Q itself. So it seems like this non-locality here in our experiments, in our numerical experiments, are more important than kind of this chaotic nature of the system. Okay, so I want to now change gears a bit and talk about another optimization problem, which is this low autocorrelation binary sequence, whereby you're trying to minimize this classical Hamiltonian here, which is essentially a sum over some autocorrelations, and then you square it, which basically gives you highly non-local four-body interactions. And so the idea is, if we have a classical problem which already includes this type of four-body terms, we may also get an advantage when including them in our annealing schedule. And what's nice about this Hamiltonian here is that it's fully deterministic, so we don't have to keep drawing and try to find hard instances, but we really only have one instance that we need to consider. And it does feature some say, essential properties of disordered systems, which people usually refer to as self-induced disorder here. And so there's really no classical algorithms known that give you exact answers here that do not scale exponentially. So this is really a hard problem to solve classically. And the world record for giving you the actual true ground state of this Hamiltonian is given by 66. So really a small number, and even heuristics can't go much, much further beyond that, because even the heuristical algorithms scale exponentially. And so I think this Hamiltonian here is a very nice testing ground for quantum advantage if you have, say, roughly an order of 100 logical qubits. And so now we want to test if our bosonic annealing schedule gives us better results compared to the transverse field. And what we do here is to compute the time to solution for varying annealing times and varying systems, system sizes n, which we compute here according to the standard formula. And then we compare the two different annealing schedules. And here on the right-hand side, these three plots show you different scaling behaviors for different annealing times. And first of all, I should say, you should take all of these results with a grain of salt. They are made only for very small system sizes, so 9, 11, and 13. So extracting the scaling behavior here is certainly quite sketchy, but nevertheless, it can give us some insights into whether the bosonic SYK Hamiltonian can perform better. Okay, and we can see here, at least for these intermediate and also longer times, it seems like the BSYK curves here, which are these orange ones, they do scale better compared to the transverse field curves, which are shown in blue. And if we plot the scaling exponent B as a function of annealing time for both transverse field and bosonic SYK, you will find that precisely in this intermediate regime, the bosonic SYK driver will give you a significantly lower scaling here, which is certainly some more indications, at least, that these chaotic type of or non-local type of driver Hamiltonians can give you an advantage. Okay, so what are the challenges if we actually want to implement this in hardware? And there are two main challenges. The first one is that our interactions must be non-local, which can be done very nicely using the all-to-all connectivity capabilities of, say, trapped ions and Rydberg atom arrays. The other issue that we have to face is that we need these Q-body interactions. And here, very naturally, you can think of Rydberg atom arrays, where you essentially move multiple atoms into the same entangling zone, and then you shine some global laser light on them, whereby you really implement you implement this Q-body interaction sort of with a single gate. Okay, so I guess the question is, how many C0 gates do we need to implement to really study this dynamics of the bosonic SYK Hamiltonian? And for this year, we optimized the number of C0s using standard techniques here for all of these different type of SYK models. So the full fermionic one, the bosonic one, and then also some sparsified fermionic SYKs and the sparsified bosonic SYKs. And you can see that for at least this sparsified bosonic SYK model, the scaling here is quite nice. It goes linearly. And everything that's shown here in green is essentially, I would say, a regime that you can access very nicely even now in these days, where one Trotter step basically takes you for, say, 20 sites, roughly 300 to 400 C0 gates here. Okay, so let me quickly summarize and pose some open questions. We found that adding these non-local terms to the annealing schedule can really help enhance the performance, in particular for hard optimization problems. And now some open questions involve, in particular, if we can sort of make the connection clearer between quantum chaos, the sparsity of the model, and the annealing performance on, say, a more formal level beyond this very heuristic approach that we did here. And also, how does this ratio of affected instances depend on n? When I make my systems larger, do I still get a significant proportion of these BSYK Hamiltonians, which give me an enhanced performance, or does this rapidly decline as a function of n? And of course, you can also think about different quantum algorithms, say the QAOA algorithm, and then consider non-local driver Hamiltonians here. We might also get some performance boost in these situations. And lastly, it would be interesting to really kind of quantify and disentangle the effects of non-locality and this additional non-commutativity that we have in the bosonic SYK Hamiltonian, and compare this to, say, non-local terms, which are just in one basis. So let's say sigma x terms, which we simply add in a Q body fashion. Yeah, and so just to conclude, I think this is a really promising route towards gaining advantage over the simulated quantum annealing, quantum Monte Carlo approaches, and hopefully also something that can be implemented in the near future on, say, logical qubit machines with, say, 100 qubits. Okay, so let me thank everybody that was involved in various discussions here, and of course, Subir, who hosted me in the past semester. And now I'm happy to discuss if there's any questions.
Great, thank you very much, Henning. Thank you on behalf of the audience. And yes, this discussion is now open for questions. So if you have a question for Henning, either raise your hand or just speak up. I had a quick question for clarification. Can you maybe go back, maybe just one slide? There was something I didn't quite understand.
Yes.
Yeah. So I'm trying to understand how what the affected ratio means. Because
Okay. So
if I look at the graphs on the right, it looks like always you're to the south of the dashed line, which means you're always gaining an improvement. So what am I not understanding?
yeah, that's right. So what we plot here is really only the cases where we do reach 90% within this window of our simulation. And of course, there will also be instances which will lie somewhere above this, but we did not access those and we did not try to extrapolate anything.
Understood.
So we are only showing these successful instances here, which surely gives this plot a bit of a bias. And that's why it's important to look at these affected ratios, which vary somewhere between 30, 40, 50% here, where you get these kind of enhanced performances.
Understood. And so maybe if I can have another quick question. There's a weight which I guess you call capital J in your SYK Hamiltonian. Comes in front of the Pauli's, I guess. Do you need to tune that weight, or is it just like +1 or -1 or something, or how have you optimized that?
Yeah, right.
A Q order interaction.
So usually in the SYK setting, you normalize it in a certain way. And that's also exactly the normalization that we chose. Now, what you could also do is some bimodal distribution or some uniform distribution. In our case, it's a Gaussian distribution around 0. And that also, according to some experiments that we did, gives you the best performances.
Okay. But I agree with your last comment that we need to see what the roles of the various X's, Y's, and Z's in your second or fourth order SYK model is. I suspect it's the X ones that are really important, but maybe I'm wrong.
Yeah, absolutely. I mean, you can also think that if you have these additional non-commutativity and additional kind of interference effects because of this quantum fluctuations, it may help. But it's certainly important to figure this out. I agree with that.
Sure. Any other questions from any other member of the audience? If not, let's thank Henning once again for a very interesting presentation. And I guess I should point out that we're now taking a Christmas break from the weekly INQA seminars. We'll be back in the new year, probably on the 14th of January, though possibly on the 7th of January to be confirmed. So check your emails and messages about the schedule, and I wish everybody a happy holiday and best wishes for the new year, and I'll see you in 2025. Thanks, everyone. Bye-bye.
Thanks a lot, Paul. Bye-bye.